today's session is about our availability and scalability cubes. So these are frameworks to help you scale your architecture when you run into problems, either with velocity or with time to market, or you see bottlenecks in your architecture. So it builds upon the ones we just had recently. Anti-patterns was last week. That video is posted on YouTube. And the one before that, the risk model for availability. We will revisit just some of those concepts in this particular session. Again, don't forget to subscribe to our YouTube channel. We're up to the 30s now for subscribers, and we're getting faster about posting these videos in here. Almost all of these also have articles, blog articles that will help you too if you don't want to go listen to the entire webinar. Please like and subscribe. Scale Cube. Most of you that know us, this little cube in our logo here is our branding, and it was one of the original IP created by the founders when we helped companies. And it was really when the founders left one of their startups and they applied the concepts they learned at eBay and PayPal to several B2B providers and also B2C providers about ways to scale the architecture and the organization. So we'll walk you through our cubes. There'll be an X, a Y, and a Z axis. You don't have to remember what is X, what is Y, and what is Z. Just remember there's different dimensions, and there are different ways to simplify the problem space. Starting with our scale cube, at the bottom left corner is a one monolith, one system, and on the far right side is near infinite scale. We'll walk you through. It's geographically distributed, functionally split up, lots of redundancy throughout. When you start your company, you're typically in the bottom left side. As a startup, you should do that. It's a lot of work to split up your architecture. Over time, it then makes sense to split that up. But when you're a startup, you want to prove that initial market fit and make sure that your product is viable in the market and it's also technically feasible. X-axis, this is redundancy. Basically, duplicate everything. This allows you to horizontally scale, although there are limits there. So this is all the way from the calling service all the way down to the lowest level of wherever state is stored within your environment. Looking at this, a single one, you have a presentation layer, again, a browser or an app, going through an application layer, through a database layer. Probably start out just with one, may not even have redundancy, where you're moving towards redundancy at your application layer and ultimately at your database layer. And in this view here, the database is really a clone and load balanced. It's identical to another one. You're probably using a managed database service that does the backups and has them in another location, maybe at a recovery point in time. And there's typically a time to fail over from one to another. But that's the X scalability. It's going to apply when we show the availability cube, similar type concept. Pros and cons. This is the easiest one. Most companies do this even early on because you want that redundancy. It's very fast to implement, and it does scale fairly well. The cons are that if you duplicate a lot of your storage layers, that can get costly. And the more and more copies you have of your data set, it's going to cost more, including the application layer. It also doesn't address cacheability very well, meaning what's in memory on the app servers isn't always likely to have a good cache hit ratio at this layer. Now, we're going to walk you through ways to add a cache at this layer, but the likelihood of the cache hitting in your transactions isn't always as high if you just focus on the x-axis. Let me pause there. Any questions about the x-axis from the audience? All right, pretty straightforward. So Y is functional splits. The bottom is no splits, and Y is functionally splitting similar ones. So the examples we had on previous ones, we showed an e-commerce example. Authorization is a common one. Search is a common one. Reporting is another one. These are items that are pretty common to split out. The idea here is an outage in one part of your architecture does not impact others. There could be some disruption, but it means the application is still functioning in some aspect. So going again from that one team dealing with one service in one database, splitting out by teams. So each team can work on their own services, and we're showing the verbs as the service layer and the noun is the data. And recall we have those dedicated databases for each service. That means they're fault isolated, but again, the teams can operate independently. So pros there, scales transactions very well. cost, you can scale independently. So if you need more in search, you just spend more in search. You do not need to spend more across the entire stack as you would. So if you don't do the split, you're unnecessarily paying for a lot of compute that's not being used. This is also the only one that allows the organization to scale. Otherwise, as we talked about before, too many people in the same code base, you start slowing over time if the code is not well structured. This does improve the in-memory cache hit rate, and it also improves availability because you can have that fault isolation. The cons, though, as many of you know, it takes time to architect. When you get to this point, you'll probably need to do domain-driven design, event storming. You'll want to have telemetry to look at how the calls go all the way through your stack to know where to safely do it. And it's complex because you now have more things to manage. So let me pause there. Any questions about the y-axis? Show of hands, who's gone down this path in your environment?
Eric, would you share what you guys have done in splitting out your services?
Yeah, so we're a data ingestion heavy application. And so we've had everything on the same box forever, and it's always, legacy code, like I'm sure a lot of people are dealing with, and it's always, oh, I can't touch that because it might affect that. And so we're breaking out each step of that data ingestion process and into its own separate service, separate boxes, separate database. And yeah, it's going really well, and we're actually starting to see some velocity increase because of that Y separation of teams.
Was that difficult to do the Y separation?
Oh, absolutely. But we did an event storming activity that helped out kind of figure out those domains and get them tight. But if your domains aren't tight, it's absolute hell.
Absolutely. It does identify a lot of potential tech debt areas that you want to get rid of. So it's something at some point in your company size, you'll probably have to do this. All right. Z, the last one. This is sharding, usually by some grouping of customers, most commonly by geography. And the idea here is an outage of one area will not impact the others. So you've decreased your blast radius in this dimension also. So the example here is, let's say you've got folks in Montana, like not a lot of users there, and then some in North Dakota in this example, and then a lot, for example, in New Jersey, all calling a data center in the West. So the idea here is you might have high latency for folks on the East Coast calling the West Coast. Where splitting to an environment where you have your local nearest region, you would split a third of your traffic to the west, a third to the central, and third to the east. You might have more traffic in the east, but that allows you to scale up in the east and maybe not as much in the central, maybe more in the west coast. But you also get the benefits of higher performance in addition to the smaller blast radius. So pros, also scales transactions well, reduces response times because you're moving closer to the user. There's fewer network hops. And we'll get to your question in just a second here, Nicholas. Also improves the cache hit rate, maybe not from a functional, but it's more likely that those customers are in memory. You can also have fault isolation. And this is another one that also allows A/B testing to deploy things into different environments by geography. This is also difficult to architect, and it also has more things to manage. So you're probably going to need infrastructure as code in order to manage this option here. All right. Good question from Nicholas.
Let's read the question so everybody understands.
Yeah.
Is
So
it fair to consider a CDN, a content delivery network, as a Z-axis scale?
We consider it an X-axis scale. And so we'll give you some examples here, but within the X-axis, you can actually split it up a bit more. But a CDN is usually a different tool, and it's automatically doing the work of figuring out what you want to cache or push to the edge versus pulling it back. So the CDN does give you geographic improvements because you're pushing the big heavy content, ideally that's static, closer to the edge. But we view it more as an X one because it's a faster thing to implement in your architecture, usually than over a functional split or sharding split. But we're going to walk you through one of our handy dandy decision trees soon. And a CDN is a very good option, though, to scale quickly. So looking at these in combination, again, X, duplicate everything. This is redundancy. And recall from our availability math that the more things you add in parallel, the higher the availability goes up because you have more things in parallel. But that comes at a cost trade-off. Y-axis, again, you're functionally splitting things. And then the Z-axis is sharding by different customer dimensions here. So you'll have to organize your customers in some way to split those up. So looking at all of them to general, X, you're typically going to split up your web, your app, your database tier. And so in the web tier, you're replicating your web servers, your load balancers are here. This is where we would consider a CDN, putting it up here. The app tier is introducing caching. So having an object cache here, that's something that you can do. So we view object caches also is in the X-axis. And the database, we also consider a read-write split of the primary database an X-axis split. You arguably could say it's a bit of a Y-axis, but really it's generally, we consider that X-axis because you're doing it perhaps at the database level. It's managing the read and writes. You're going to have to redo some of your code to make sure that you're calling reads versus writes and not hitting the wrong instance. But we do consider a read-write split as an X-axis split. Y, each service has its own database, and then Z is different pods. In this example, we're showing 2 in North America and 2 in Europe. All right, so an example here, this is a Z-axis. This example would probably be, and we'll show an example, this applies to B2B or B2C. So if you have a subdomain, and this is more common in a B2B space where you'll give someone a URL, probably may not be geography, but it might be for a particular company, my company / your company, and then it'll route that person. In this example here, the person would typically be anchored on the West Coast and they're traveling to New York. So if you don't have a subdomain, ideally you'd have a cookie. If you don't have a cookie, then it would do a lookup for the person. So it would take a little bit longer. So there'd be just a little bit of a delay just on the initial authentication here for a user that would typically be in one environment versus in another. So we do see some clients that are large multinationals, and initially they will split up their customers by wherever the bulk of the workforce is. When you get into a B2B space where you have multiple people in multiple regions, you might have to actually split up a single tenant within different regions. Much harder to do, but you'll have to have a lot more knowledge of the customer base in that case, though. So pausing here, have any of you done a Z-axis split where you shard your customers into different pods? Seeing no hands, is anybody considering doing a Z-axis split or sharding of customers?
We have a scenario where we have a few customers that have contracts that their data can't leave the United States, but we have teams in India. And so we're looking at doing a shard based on that.
And how do you keep, so the data stays in?
Yeah, the US team would be on the, we have a US team and an India team. So the US team would be the only one that has access to the shard with those 6 customers. And then the India team would have, and the US team would have access to the rest.
Got it. Yep. Yes, we commonly see that for folks that either for data residency or just security in financial services. This is very common too. All right. So this is our handy dandy trusty rusty scale decision tree. And typically in this first box is, do you need to scale very quickly because of constraints in your architecture? So we're going to walk through the left side first. And the first one is, where is the constraint? Is it in the application or the database? If your application is being constrained, you typically will want to try to remove sessions. So we'll talk a little bit about state later. So that is a way to alleviate contention on the database, on the application. A CDN is also helpful here because that should reduce load on the primary application server. The next one is the database. So is there a high read to write ratio? And if there is, then you would want to consider a X-axis split of the database. This also applies for NoSQL databases. A lot of the managed services allow this kind of split. So if that's the case, that should give you some headroom. The next question is, if you can't do a read-write split, then consider, can I easily split up my customers geographically? And so if yes, then you would be in a Z-axis split here. So let's go to the right side here. On the right side, this is where, are we slowing? Is velocity slowing? We have too many people dealing in the code base. If yes, do a Y-axis split. If no, you're still not, for example, the teams are still able to release features. Are you having some availability issues here? Is the load distributed? We have some more details here, but is the load distributed between your different services? And if so, then you can actually do an x-axis split if it's pretty distributed load across the different functions. If no, are there also discrepancies in the workflow? So is it, for example, you have one aspect of a workflow, either the beginning or the end or the middle, where they have different availability and you're trying to string together a long transaction. In that case, you'll need to do a y-axis split at that point. And that's one of the trickier things to do, but this is the example of a y-axis split here. So the main thing to think through, though, is where are the bottlenecks in the architecture and where are the bottlenecks in the teams? And as you go through this, once you do some discovery in each of these, you actually may take a different branch because what you thought where you were on this decision tree, you might be somewhere else. So any questions about this decision tree? You don't have to memorize it. We'll have it in the notes. But again, it should just be an easy way to think through when I need to scale, what are some of my options? All right. Looking at these in play here. So z-axis, you have a customer split among geographies. Those are load balanced here. The y-axis split within a geography. Again, we talked about login service, report service, whatever service you have. And then the x-axis is cloned. You might clone those, whether that's your app layer, and then the database x-axis split is a read-write split. So we could also layer in caches in here between the application and the database. We could also add in a CDN up here at this top layer here. So any questions about X, Y, or Z? How many of you feel like you've maxed out your X-axis options? How many of you are doing read-write splits? Only Eric. Very good. All right. When you get into Y-axis splits, you're probably going to need at some point a messaging bus, a way to get the data that's needed in one particular function to another function. This is where you get into event-driven architectures. Recall from our last session that we had in the anti-patterns that one of the patterns that we want is dumb pipe smart endpoints. We don't want a lot of logic in the actual in the pipes themselves. You're typically going to need smart subscribers on either end, and you'll probably need a data lake at some point to pull that data off as needed. So that leads us to our scale cube for messaging. So you're going to implement a messaging layer if you get to that point. You're also going to want to think of splitting that up either by how many do you have redundancy? So the x-axis would be, do I have a clone? In this case, you'll probably need to have a managed service to manage that. Y would be different topics or different ones. And then Z is, do I also need to split it up geographically? So same kind of concept, but we do see people go down one of these splits and don't think about the messaging layer. And if you don't think about the messaging layer, you're going to have availability issues and performance issues because something could fail or transactions could take too long to get from one particular service to another service. The availability cube will be pretty fast. So very similar to the scale cube. It's just looking at it from an availability perspective. Bottom left, a single service, highly write, highly available. Again, a lot of the same concepts, but you'll see what you're trying to solve for is where this cube comes into play. So again, X, redundancy everywhere. So failure in one point means others can pick it up here. So it's redundancy is what we're focusing on here. So same as the scalability cube here. But again, the idea there is how much can you improve your availability via the redundancy, not necessarily by increasing load. Pros, same thing as the other one here. Easy, fast. You can raise, we'll show you what the base is of the probability of failure. But the cons, again, it can be costly and it's just multiple deployments that you need to manage. Why? This is where the difference is here is, do you have those broad or deep call chains? This is where you are at the bottom. You've got a lot of calls that have a lot of anti-patterns that we talked about in the last session. You're in the higher end of the scale if you have no deep call chains. So the idea is you want to eliminate your calls in series, your fan outs, your fuses, your meshes, all of those anti-patterns that reduce availability. So when we have the top one here, this is calls in series. Remember, every one of those calls reduces your availability, and each one that you add makes it worse. And every one, it's always worse than the lowest available item in the items in the series. The fuse here, this is two services have it calling the same service synchronously. And then the fan out is the one on the top where one service is calling two, and it's waiting for responses for both of those. So again, all of those behave the same from a math perspective. Your typical solutions are going to be splitting those into services, subscribing to message buses, or if you can deploy libraries to those services, the idea there is that you've reduced those hops. And so you just deploy them on the same compute with that service there. So again, independent services, no deep chaining. So when you're thinking through this, a lot of our clients, when they're thinking through the y-axis split, they're thinking of velocity, but you also want to think through availability when you're splitting up your architecture. So do both at the same time if you're going to go down this path of splitting up your services. So again, the same availability, same benefits. You improve availability because you have a smaller fault isolation. You reduce that cascading effect of failure. Costs are the same, and you improve the cache hit ratio. Also, it's difficult to do, and it does make it a little harder how you deploy services here because you're focused on availability. All right, and then Z, we talked about before, same as before. It's the fault isolation of your customer segments. So one fails, they all fail. In this case, you split it up. And so if you're, for example, running Azure in the Midwest and that Azure region goes down, you're only impacting customers in that region. As an Office 365 user, I've seen that several times. I don't know if many of you see that yourself. Looking at the cubes all together, X, again, redundancy, just like the scale cube. Y, you're eliminating those broad and deep call chains, and Z is splitting out those customer segments to reduce the blast radius. So again, think of this. This is where the cube concept is helpful, thinking in 3 dimensions visually. So on the X axis, you've reduced it by whatever that particular axis is. Y, if you've cut it into 2, you've already reduced your blast radius in 2. Z, if you cut it into 2, you've also done that. But when you take it to the 3rd dimension, it actually is even better. You've reduced it by, if you can do 1 split of Y and 1 of Z, you've reduced it by 1/8, okay, not just 1/4. So think through that math. So again, the math here, uptime, you've got uptime is all available time minus downtime. That's your percentage. And so this is just for calculating the clock. And remember, for multiple nodes in parallel, it's 1 minus that number here. So looking at the math here, there's the base and then the exponent. The base is the availability of those individual items. So how many instances do you have? And remember from the decision tree, is your code good? Is it high quality? Your infrastructure, is it fairly new, not too new where it breaks, or too old where it's going to decay? How well you can monitor and detect something, because that will reduce the downtime. How resilient it is from a redundancy perspective, and how well you do error handling. So that is the base number. And the exponent is all about those anti-patterns that we talked about. Every anti-pattern increases that exponent. So the depth of the call, the breadth of the call, remember however many devices it goes through, however many hops it makes, and however many of those calls are synchronous. So some redundancy there, but just think through how many hops there are in your architecture. And that's the way you can quickly estimate that number. So this is your downtime number again, however many minutes you get in a quarter or a year. And then this is we gave this example here. We used e-commerce, but this one is just 6 services here, calling a single database. And in this example here, we had all those additional hops we talked about between the router and the switch and the load balancer. That's why you had to add that exponent multiplied by 3. And this one is here, 10 services multiplied by 3. It's 6 times 4. That's where you get to the 30th. And so in this case, you're already at 97% availability. And the idea here is each one gets its own database. You reduce the depth of that. So you went from 4 nines to the 30th to, in this case, to the 12th. And so now you're back to 2 nines of availability. Not great, but it's still better than it was before. All right. Any questions about the availability math? And if for some of you that missed the availability math 2 sessions ago, we have that recording, but if there's any questions, I'll pause here. When you get into your y-axis splits, and even before there, the idea is to try to have a stateless system here. And the reason that we care about this is that if you have to store state and you need more and more parts, it's going to cost more, but the more places you store state, the higher the likelihood that something is going to break. So you want to reduce the size of the state, the probability, and the affinity, which we're going to explain this here of where the state is tied to. So some advantages, in some cases you want that persistence, the concept of a shopping cart or filling out a form and coming back to it, multiple people collaborating on the same item, or if you need to do some customizations here. So those are some advantages of a state. In this example here was the flexibility. A lot of times if you have a form, a very complex form, the user can't fill it out all at once. They want to come back. So you have to store state somewhere. And then it can help you also with debugging. You're storing it somewhere. So those are advantages. The cons are that we mentioned. It is more complex. There's more things that can break. It's more things you have to scale, and it's more costly. And if you have too many items, it's going to reduce availability. So all challenges of state. Again, we talked about cost and speed. It can slow response times down. And in some cases, it can introduce security risk. So desired outcomes, wherever possible, we're trying to minimize session state, application state, and connection state. We want to be as small as possible. And I'll walk you through this a bit more. There's some details here where you can see these examples. But every time you're trying to store state, again, you're increasing the probability of failure and you're increasing cost. So in this example here, don't worry about the X, Y, and Z, just the different aspects from the size of state, which is large versus small. So again, just think of if I need to store a very large transaction somewhere, that's going to take time versus the smaller the item, that makes it a little easier. So that's one aspect of your blast radius. So as possible, try to have smaller and smaller items from state. All right. And this one, the y-axis here is more about redundancy here. So we arguably should have split these X and Y, but the idea here is just making sure you have some redundancy if possible. And then lastly, Z, how close is this to the server, to the user? So within the app server is not as good as a database or object store, or ultimately a cookie, or ultimately at the browser level there, where you have no state whatsoever there. So any questions about this one? Because remember the idea here, we talked about that anti-pattern was if something breaks at the application layer, the database layer, it's more likely to impact all those users. Where if you lose something at the browser level, you're not likely to impact all customers in an environment. Okay, so that's what we mean by where to store state. Stateless is the far part of the quadrant. At the other end is you're storing everything and you're storing every transaction. So you will get slowing performance and slowing velocity. Ultimately, your goal is to move to as stateless as possible. So some use cases here. So a shopping cart is a tricky one there because a user is going to add items to a cart, but they're probably not going to transact. The time from when they add to a cart to payment varies quite a bit there. So you need to persist state somewhere. Ideally, it's off your primary application server. You want to move it as close to the user as possible, or you might store it in a cache. So that's your challenge, a very common one in shopping cart. And cookies are a good way to do that. A lot of e-commerce situations you'll see, if you go hop onto another browser, if you still see something in the same cart, you'll have an idea of how did that particular vendor design for that session state. Payments are a tricky one here. If you're actually managing the payment, there's a concept of a two-phase commit that you want to make sure, does the payment and the debit, does this person have the money? Has this person received the money? And then that can actually take quite a while. The idea is to split that up and split those into two transactions that are eventually consistent here. And a lot of folks, when they first start with payments, are very hesitant to do this though. So when you build actual payment systems, the way you minimize that is you're actually doing a lot of the checks up front to say, does this person have the money, before you actually go and try to push it somewhere else, and then make sure. And if you trust the person on the other end receiving it, then you're usually going to say we think that transaction is going to work. And if it didn't work, we'll have some other mechanism to go chase that down. So that's the idea of managing state. So if you see anywhere you have a two-phase commit where you're calling in other service and you're having to wait for it, the idea is to try to break this up into eventually consistent. Where it gets really hairy is in a workflow system. The idea here is transactions must go through multiple steps, and it's very difficult to unwind those different steps. And so this is where you start to get state creep. You're storing more and more state. And if you have to do, we talked about the previous one is just 2 systems, but a lot of workflow is 3, 4, or 5 systems here. So in that case, you're going to need a state machine where you have your inputs, the transitions, and until recently, it was very hard to go build these. And if any of you need a particular state machine with microservices, reach out to us independently. We just looked at a particular vendor that does this very well for microservices. This is a common one that we've seen in, a lot of the AI vendors today. When you're trying to interact, you want to make sure you keep the concept of what was the prompt, what was the response. And if you lose that particular experience, a lot of these AI vendors that you're seeing, particularly the large language model ones, you're not likely to want to go back to that particular system. So if you're interested in that, reach out to us offline, not on the webcast. So a lot of cubes there. Any questions about state? So multi-tenancy. This is more for B2B customers or B2B2C. And the idea here is thinking through the cost structure of what it costs to maintain multiple different splits. So this is usually around a z-axis split. And once you've done that, there's some more dimensions to think through. The X one is the simplest one. Is there logical separation or physical separation? Do I, ideally at a lower cost, I'm just logically separating because I can share the same compute and the same actual database, okay? Y is how deep is the tenancy? So at the very lower levels you've got dedicated network connections to your particular customers. So think of this as you might be in a cloud connecting to someone on-prem. And the more and more that you're paying for that, there's more of the stack that you're paying for there. And then the Z is how well can you split up your tenants there? So in one case, you have everybody gets their own tenancy, which is going to be very expensive, versus I can collapse a lot, but you don't want to have everybody in the same one, in the same shared everything, because it reduces availability. So just looking at it this way, again, this is all about cost structure here. So if everybody gets their own database, that's very costly, right? Everybody needs the same stack from database to application layer to, CDN. Multi-tenant, this is probably your lowest cost. You probably get better asset utilization because you can move different customers around. And this is where you can do that z-axis separation. All tenant is, again, lowest cost, but it has the high blast radius. If it's down, then everybody's down. We do see this as being okay for data warehousing or reporting because they're not really a transactional system. Now, we do have clients that are data warehouse clients. They end up actually being in the multi-tenant situation here. But for you, let's say you are a B2B and you've got a reporting engine, you might have the reporting be in everybody together in a single big data warehouse separated logically, but your transactional systems may be multi-tenant. Are any of you doing multi-tenant today? This was a z-axis split, so it's the same question. Is anybody considering doing a z-axis split?
Crickets.
Yep. All right. That means you're probably too small or that you don't need to do one of these splits. All right. So this is just an example here of when you do multi-tenant, where you would typically share versus what would be dedicated. So again, closer to the edge, it's almost always multi-tenant. Firewalls, if you can, have that be multi-tenant. And if you're provisioning this in cloud providers, you may not really know what's going on behind the scenes. And then web servers, application servers, this is where you start to get more tenancy here and swim lanes here. Last cube we're going to show today. And the only reason we're showing this cube, we do have someone in the comment there.
Yeah, Marie, would you
Yeah.
be willing to talk about what you're doing?
Well, for our multi-tenant, it's our legacy system, and I think we've just I mean, I think it's worked well, but it's hard to scale. So we are trying to evolve that philosophy a little bit while still being able to kind of scale appropriately. So we're still really early on in the new platform. So I can't really speak to what we're going to do for sure there. But yeah, I mean, we're considering both options, I'll say. Single is, I would prefer multiple. I will say that. I will prefer multi-tenant. It seems easier to manage and easier to scale.
Yeah, and you're going to have better cost structure. All right, well, that's actually a good transition because as you're thinking through your options, we have something called the scope reduction cube. We have a lot of cubes. The idea is just to simplify, make something very complicated be as easy as 1, 2, 3. But it's not. It's what are the most important 3 items for a decision you're trying to make and to try to get it to the biggest risk drivers or value drivers. So let's use your example, Marie, of you're trying to make a decision how to split something up. So again, it doesn't matter what's X, Y, or Z, but in this case, one dimension is let's just focus on a particular business unit. This could be a particular or customer segment or particular geography. And the idea there is let's do either the easiest one or the hardest one, but don't do it for everyone. Okay. So just narrow the scope there of what you're focused on. And then Y is functionality. So again, that's more like our Y axis, which is let's start just breaking up a functional piece of it. And then Z is more about technically how you do it. On the worst one is we're going to rebuild this from scratch on brand new technology that the team has no experience with. Okay. That's the most risky. So if you want to say, I need to rebuild everything, that's the worst place to be, the greatest potential of failure. The fastest would be I leverage platform as a service. I use third parties. I look at things that I've built over time that I really should have bought now, or that a third party can provide to me at 4.9s, and I can't provide that at 4.9s. That reduces the scope. So the goal is to reduce that scope. And again, there's just 3 levers to reduce the overall scope. So try to get to as small to the bottom left as much as possible to reduce the scope before you take on a very big effort, particularly whether it's a y-axis split or a z-axis split or just a major new initiative. So again, it's the scope reduction cube. Again, this is also useful to think of in 3-dimensional space of each dimension you increase scope, increases it to the 3rd power, right? It's much worse whatever these directions you go on. So each time you can pull in from any one direction, you've reduced that probability of failure by at least 1/3. Or that's actually not the right math, but it's close to that. It's probably would be 1/8, I should say, not 1/3. We have more cubes, but we're not going to cover them today. And again, the idea of our cubes are what are the most important dimensions or levers you have to make a decision as a CTO, as an architect, to improve the scalability of your architecture, to reduce the cost of your architecture, to improve the velocity of your team. Those are the reasons that we provide these different cubes for your team. Our next session is going to be the 28th. We're going to go into just some basic architecture principles. Most of these, I would say half are probably intuitive. You've known your whole career. The other half will be some pretty neat ones that will help you as you come up with some challenging decisions. It's also a good way to remind your team, particularly those junior folks that don't know these principles. So I think Doug's going to be teaching that next session in 2 weeks. And then after that, we're just going to focus on monitoring and operations. And then we'll get more into product management. We are done a bit early today. Does anybody have any questions just in general? All right.
All right.
Thank you, everyone. Have a good weekend.
We appreciate you being here. Have a good 3-day weekend. President's Day is on Monday. We'll see you in a couple of weeks.